All right, now for chapter 4, question 4, chapter 3, question 4, we have which region is hypotonic? So again, what is meant by hypotonic? Hypotonic means you have more water, right? You have more water, more water. So I think you can see here which one has more water. Obviously, water is this one, the small one. So obviously, yes, region R has more water. So how do you explain that? You should say it has more water molecules. Or in an even more professional setting, you can say higher water potential. Okay, higher water potential. And then remember, I mentioned before, any sort of hyper, it must be compared to someone. So if possible, try to add your answer. Then region Q, region S. Try to compare it to region S. So you can see very clearly, R is only hypotonic when you compare to region S. Comparison is a key, okay, in any sort of, any sort of question about hyper. Even if you do the basic format, what water is hypertonic to a cell? You always compare to a cell. You see, comparison is a key for hyper. Now, how would you achieve a dynamic equilibrium? Yes, you have to first of all make sure sucrose doesn't move. Sucrose cannot move. Okay, no, maybe before that, where would the water flow? Of course, the water will flow from more water to less water, right? More water to less water. 多水去少水. So it will obviously decrease the water level here and increase the water level here. So you can first of all draw the water level to be higher and lower. One lower, one higher. R will be lower, S will be higher because we all know that water goes from hypotonic to hypertonic. So that's why R decrease, S increase. Then you put in all your answer. So your sucrose molecule should be still 3 over here. And the other side should be still 8 of them. So you cannot change your sucrose molecule. Yeah? You cannot change your sucrose molecule. But you can change your water molecule. Your water molecule should then be balanced. It should then be balanced. So let's count how many over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. Okay, 5 for that. Okay, cool. You have 25. So to keep it a bit balanced, you will then do something like 18, 17, no, try to just, sorry, no, what am I saying? No, 12 and 13, okay? 12 and 13, so you can divide them into 12 and 13. In this case, you can do, maybe you can do 12 here, then 13 here. Okay, there is a lot of them. There is a lot of them, but yeah, sure. Okay, so 12 and 13. And again, finally, not forget to label. This is sucrose, and this is water. Okay, that's it. Again, you can take some time to pause the video if you need to see clearly or you need to copy or whatever. Cool. The next one, what is this process? So what happened here over here? Water moves. When water moves, this is called osmosis. Okay. When water moves, this is called osmosis. Okay, cool. Let's move on to next question. Next question, we have something dissolving here and it turns the whole solution purple. So something dissolved and it turns the whole solution purple. What is this process? This is simple diffusion. Now, why not osmosis? Why not any other? Because you see, there's no a single membrane here. There's no membrane involved here. There's no cell wall, there's no plasma membrane, there's no bilayer, there's no whatever, there's nothing. There's just literally a gel, right? So in that case, you are not expecting to see, any sort of transport except simple diffusion. Because remember, simple diffusion is the only one that can do a diffusion without a membrane, right? And you can see indeed over here is quite literally from here you diffuse out simple diffusion, very straightforward. Okay, yeah. So remember, any normal diffusion outside of the biological context, outside of a membrane, is just simple diffusion. Okay, your mom cooks in the kitchen, you smell it, that's simple diffusion because the smell diffused, right? For example. The next one, how does the water turn to become purple? Yeah, very simple, because the whatever thing over here, it dissolved and diffused towards the rest of them, right? Okay, like, so I think even so, you see, even this is not like a conventional kind of question for transport, you should still know that the typical standard of a transport. Remember, you need to talk about what has been transported, talk about where has been transported, and talk about the characteristic, maybe a bit, and what else? Talk about the three characteristic. Remember the typical format. You have the molecule characteristic, you have the type of transport, and the where the site of transport, then the characteristic of the transport, right? So that few things. So yeah, same thing can happen over here. We will first start off with the potassium manganate being dissolving. The potassium permanganate crystal, it dissolve. Okay, so this thing it dissolved. And when it dissolves in the water, it will then start to diffuse. So what happened here? Yes, it diffuses. Again, there's no location, they just diffuse. They just literally diffuse throughout the water. And this is again what we know. The first characteristic, concentration gradient. So yeah, apply that here. Potassium permanganate, it will diffuse down concentration gradient. It will diffuse down concentration gradient. That's one of the point, because indeed we are following the template, we are following the format of a transport question. We have to always go through the characteristic. The second characteristic was energy. Not rewarded here as in the mark scheme, but you can talk about that. You can talk about that if you want. And finally, it was the result. What is the result of this experiment? I mean, of this action? It will result in dynamic equilibrium. So yeah, talk about that. Potassium permanganate will diffuse until dynamic equilibrium. You see, even though this question doesn't look like a proper, proper kind of transport question, there's no proper molecule, there's no proper site of transport, there's no carrier protein, whatever, but still, it is still following the concept of passive transport, concentration gradient, equilibrium, and everything. So you see, the point is the same. Even it looks kebab or whatever, you should still follow the same point. Yeah. Okay, cool. Finally, just a quick conclusion. You can also just quickly say that in short, what happened here? In short, basically, your potassium permanganate, they distribute throughout the water. This is a short conclusion here. It distribute throughout the water uniformly. Okay, it distribute throughout the water uniformly. Okay, that's it. Let's move on to the next question. Okay, again, if you need to, I don't think I will try to pause too much in this kind of videos, because I want it to be fast and intensive for you guys. Okay, you can just watch it quickly and then move on, like that. I don't want to take too much of your time. So yes, please feel free to pause if you need to. Now let's move on to the next question. This is a cell in whatever this is called, and it says that 100% of glucose and amino acid are transported into blood capillaries. Once again, 100% of glucose and amino acid are transported. 100%. This is a complete removal of the glucose. So yeah, I hope they give you a bit of hint. And they say there's a high density of structure X. Do we know what is structure X? Well, that is quite clear. 看到 unknown, 给名字, we can first always start with this. X is mitochondria. I think that's quite clear, because indeed we can see very clearly this is a mitochondria. So if you have a lot of mitochondria, why is that so? Right? Think about that. Why do you think you need so much mitochondria? Well, it kind of goes back to here. Remember, how do you achieve 100% removal? This is obviously active transport. And what do you need in active transport? You need energy, ATP. That's why we are having so many mitochondria. So similarly, if you don't have so many of the mitochondria, what will happen? There will be less energy. Again, you just follow this. Just follow this, just follow this logic over here. ATP, active transport, remove glucose. So now, if you have less mitochondria, less energy, or ATP, then what happens next? Active transport. Yes, less active transport of glucose. To be fair, it's glucose and amino acid lah. It says glucose and amino acid, but the diagram only shows you glucose, so well, up to you. You can put amino acid also, since the question says both of them. Yep. So there will be less transport. Less energy, less transport. Finally, link it back to the question. The question did tell you already. You are supposed to completely remove glucose and amino acid So what happens if you don't remove? Think about that. What happens if you don't remove the glucose then? Yes, the glucose will be there. Glucose and amino acid, they will then remain in the urine. Because you cannot completely remove it, it will then remain. Maybe you can put the word some, maybe just to be a bit careful here. Some of them, not all of them. Okay, some of them would be remaining in the urine. Okay, that's it. Good. Last question. You might not know what happened here. Why do we have a sort diagram? Why do we have why are we doing this? But again, this is, as you can see here, this is a method of preservation. I hope that can give you a hint over here. If you remember, we did use salt solution to preserve vegetables. So what is the action over here? Remember, this is by the concept of osmosis. This is hypertonic. This is hypertonic to the cell set of the vegetable. Hence, if this is hypertonic, you can then make the water come out. Water diffuse out of vegetables by osmosis. Okay, this is again a very standard kind of solution, very standard kind of question. Give you the solution, give you the cell, just talk about hyper. Talk about hyper. Then what happened after hyper? Yes, why do you think you need to make the water come out? Because you want to dehydrate the microorganism. So the microorganism would be dehydrated. Okay, will be dehydrated. So they cannot grow. The microorganism cannot grow, then there would be dying. Then your vegetables won't be, they won't be died. They won't be dead. Okay, cool. That's it. Okay, if all right, let's move on to the next question. Thank you very much. Okay.